Introduction to Containers with the High Performance Research Computing Group. I am your instructor, Richard Lawrence. It seems that most people who are attending this are doing so on Zoom. We have anyone here who's live today? Any live students? Okay. Live students do exist, so I may look in either direction. Today I will be teaching you about containers, and in particular, we're featuring Singularity on the Grace cluster. If you do not like the Grace cluster, you can do the same thing on the Terra cluster. But you do need access to at least one of them in order to follow along with today's exercises. Today, I will be starting by telling you about containers, then I will tell you about Singularity, and then we will learn how to use Singularity to work with containers in two ways. One is getting your containers, and the other is using them. This is the basic part of the course. Later, there will be an advanced part of the course where we do some more narrow use activities to learn different features of Singularity. So most people these days are not yet familiar with how containers work. Maybe they've used a container before, but probably just because someone told them to, they didn't really understand it. So I'm going to try to help you understand it. And maybe your life will be better, and the next person you tell to use a container, their life will be better. There are learning resources. Everything I show you today is going to be somewhere here. Our wiki has most of these topics as well. So let's start with talking about containers. What are containers? Okay, so a lot of stuff on the screen right now. What I'm trying to do is compare and contrast how containers work relative to these other two ways of doing things that you're possibly more familiar with. So on the left here, we have what I would call just installing software on your computer. So at the bottom is your hardware, and then you install your operating system, and then you install your libraries, which are the commonly used things. So for example, something like a compiler tool chain might live in that category. And then you install your binaries, which are your executables. And then finally, the user application is when you click the button to make the binaries do the thing they do. Now, if you don't own the machine, then you probably don't have much control over the operating system. So you might say, I'm going to try to separate my part of this from the part I don't own. So in the second column, we have what's called virtual machine, where you bring your own operating system and install everything on top of it from there. And then the host machine has a virtual machine manager that translates between the real operating system on the machine and your virtual operating system. So virtual machines make a lot of things possible that would not otherwise be possible, but they're really clunky because now you have two copies of an entire operating system on disk, and that's a big overhead, especially if you have to have a lot of copies of a virtual machine running. That's a lot of copies of an operating system. So the next solution is, what if we just try to minimize the amount of stuff we have to bundle up? And this is called containerization. That's where you identify the minimum amount of things that you need in order for your application to run, and then you delegate the maximum amount of things to the local hardware operating system, and the container runtime translates between the two. In this case, you don't duplicate the operating system because you know the host has an operating system. Now you just need a way to interface your libraries with the host operating system. The container runtime is the tool that's smart enough to make that happen. So with containers, if you need to duplicate this and run many copies of it, there's a lot less overhead. So you can successfully run more copies of the container given the same resources. So how many container runtimes are there? There are many. So we have a history that goes back to the early days of Linux. We have a container called LXC in 2008. It's not really the early days of Linux, but LXC is based on something that was itself based on something all the way back to the early days of Linux. This is just the first one that's like practically usable. But nobody really cared about containers until Docker in 2013, and Docker is extremely successful as a container runtime because it made that process of minimizing your amount of libraries to transfer to the host machine very simple. It does that very well. So you could bundle up really tiny packages and send them to different host machines. And so a lot of different fields of research are using Docker even now. Most containers that you find in the wild will be Docker. But Docker isn't perfect. It doesn't have all the features we would like. And so after Docker, more containers began to be developed that have more features. So depending on which features you need that Docker doesn't have, you'll select one of these other ones that are all like, they do the same thing, but better. And by definition of better is a sort, of course, subjective. So really what it means is you pick the one that has the feature you need. So let's talk about those features. So a container comes in two parts. The image is the part of the container that you build, and it is all of the parts of the environment, the library, and the applications. I said you build. What I really meant was experts build these. You don't build these. If you were going to build an environment, you would have just installed it on your own machine. The point of a container is that it's supposed to make your life easier. So you will let the experts actually do the work of building the container, and then you send the image to the host machine. The host machine has the other half of containers. The other half of the containers is the runtime, which has to be installed on the host machine. And that's the compatibility layer that translates between your container image environment and the host operating system environment. And again, because it has to be installed on the host machine, that's also something an expert does, so you don't do that. Which means whenever you wish to use containers, you have to ask the administrators, hey, which runtimes have you installed that I'm allowed to use? And then whichever runtime they have installed, you have to pick an image that the runtime knows how to read. Why do we bother with this? So containers have some advantages over traditional software installation. So here's 3 advantages. Shareability. The image file is pretty small compared to the old way of doing things. So it's pretty easy to say, upload it to a repository on the internet, have someone else download it. And it will work for them, provided they meet some basic conditions, and it's not a huge drain on their resources. Portability, because the runtime does the hard work of translating, a given image will be compatible with a very wide variety of host architectures. So there are many kinds of Linux, for example, and most of them have an architecture named x86-64, and one Singularity image could be compatible with Singularity runtime installed on all those different kinds of Linux. And the third is reproducibility, because container users are largely unaffected by changes to the cluster environment. If the administrator wants to uninstall a bunch of stuff and install different things without asking you, it doesn't really affect your life very much, because the only thing you need is that there is a runtime that exists. Doesn't even have to be a specific version. If you were depending on administrators to install the libraries and they decided to change them, you'd be in trouble. And if the administrators install a lot of different libraries, then you have to learn how to pick the right one, and that's extra work for you. So that if any of these appeal to you, then you might be interested in containers. Now, we're going to talk about Singularity in particular, because Singularity is the runtime that we have installed on Terra and Grace here at the HPRC group of Texas A&M University. So here's what you need to know about Singularity. Singularity is a container runtime. Singularity can read and convert Docker images. Ooh, big sigh of relief, because earlier I told you most containers you find in the wild will be Docker containers. That's what people have been using. So if someone wants to give you a Docker container, you can take it and Singularity can read it. So your life will be easy. Well, it should be easy. Of course, things can go wrong, but in theory, your life was easy. Now, here are some Singularity features that are different than Docker. This is why we picked Singularity for our cluster. The file system inside the container is isolated, which means if you are running a container and you need to create some files, then you have control over whether those files are going to go to the host file system, or if they're going to live in Singularity's ephemeral file system that only exists in the container and not in the host file system. So any changes you make inside the container will not affect the host file system. And therefore, most applications that aren't aware of these kinds of things are still perfectly safe. Next, the user, your username, is the same inside the container as the user outside. So that is important because, for example, in Docker, most containers, when you want to use them, you need root user permissions, because that's how those containers are typically built. And you do not have root user permissions on a cluster, a shared cluster like HPRC. So we need a runtime that allows you to do things even when you are not the root user. So as a normal user, you can use Singularity, and therefore that Singularity containers are suitable for use on clusters. So the next one is, well, other things. Singularity containers are suitable for use on clusters, and in other ways we'll get to later, there are other features that make that true. We'll go to the next bullet. Singularity runs close to the hardware for speed. And so what I mean by that is, whenever the administrator is installing Singularity, Singularity is aware of the host operating system libraries, but it also has a very good understanding of the physical hardware devices themselves. And so in some cases, it can bypass the host operating system libraries to control those devices directly. It's just eliminating one more middleman and helping your software run faster. A good example would be GPUs. Singularity integrates natively with GPUs, so you don't need to ask the operating system libraries to do it for you. It's just cutting out one more middleman in the chain. And next, Singularity works with high-performance cluster technologies. Another example of a high-performance cluster technology would be something like InfiniBand, which is a kind of network infrastructure for rapidly transferring files between nearby machines. That's important for a cluster because all the machines have their own small file systems, but they have to share a common file system. And so network transfer speeds can be a bottleneck for cluster computing, and Singularity knows how to use the cluster hardware, so you don't have to worry about that either. So here are some summary of some stuff I've just told you, I guess. Singularity addresses the security concerns about Docker. So because Singularity grants the user no additional privileges or permissions, you can't harm the cluster by using Singularity, nor can the other users harm you. So that means that it's safe for use on a shared cluster. And then independence, Singularity does not require root permission, so you don't need to ask your administrators for help installing anything. Everything you do on Singularity, you'll be able to do with your normal user permissions. I like the independence part because if users know what they need, they shouldn't have to wait around for someone to help them. They should just be able to do their work. Now, in particular, using Singularity here at HPRC, we have some advice for you, best practices. So the first is Singularity activities are CPU intense. So you must use a compute node for Singularity activities. You cannot run on a login node. Singularity is not even installed on the login node, so there's no point trying. We'll get to how to run the compute node during our exercises. The next bullet point, Singularity image files, the extension for those is SIF, which is literally just the Singularity image format. They're flat, and the word flat here, I defined it myself. What I mean is they don't share layers with other image files. If you're used to Docker, you may have heard of layers. If two Docker images are similar, then the common part of them will only exist on disk in one place. So that saves you some disk space if you're constantly updating an image. But Singularity doesn't have that. Every image file is a whole complete copy of the image. Therefore, it's not great if you're continuously updating. You don't get to keep all of your separate copies and save on disk space. But it is good if you're going to be copying that image file from place to place, which is the case on a cluster environment, because if you are on a separate file system from the one where the image file was originally built. So you don't have to worry about whether you're copying the layers correctly. The whole image file is the whole image file. But it does mean that they are large on disk. So you cannot keep them in your home directory. Your home quota on Terra and Grace is probably not large enough to handle this stuff. So you'll have to use your Scratch directory, which has enough of disk quota to handle this stuff. And then since they're large on disk, file transfers will take some time. Occasionally, you may need to be patient or use a slightly more advanced file transfer protocol, depending on the size of your container. But of course, we'll help you with all of those things. It's been about 20 minutes, and we haven't done anything yet, so we should get on to the exercises. So the exercises are going to be on the HPRC portal. Well, I'm going to do them on the HPRC portal. I'm going to use the Grace portal. So let me show you what the Grace portal looks like. That's this one. So Grace portal, well, for some reason, it's huge. It's too big. I made it bigger, but I made it too big. There we go. That's about right. So this is the Grace portal. You have different tabs for doing different cluster activities. I'm going to be using the Grace shell access so that I can do some shell commands. If you don't like Grace shell access through the portal, if you have your own terminal at home, like MOBA Xterm or a Linux or Mac terminal, you can use that. That will work for most of these exercises. But there is one exercise that's optional later where I'm going to use like one of these features. So if you do choose to follow along on the portal, it will be to your benefit. Please do, if you're at home, log into your VPN, get ready to connect to Terra or Grace for the exercises. If you've not connected to Terra or Grace before, then now is a good time to speak up in chat and ask questions. It looks like there was a question in chat a few minutes ago. How is Singularity better than Docker? Singularity has more features than Docker, and those features are specifically tailored for doing work on a shared compute cluster. For example, HPRC has 2 shared compute clusters named Terra and Grace. If you're not interested in working on a shared compute cluster, then there may be a different container runtime that has features you like better. For example, if you're running containers in the Amazon cloud, then you may say that one of these other container environments is easier to do that particular task. So better is, of course, subjective. It's more a matter of you can't use Docker here. So being able to use Singularity is better than not being able to use Docker. I don't see any questions about having trouble getting a shell terminal, so I'm going to tell you about our exercise. In order to tell you about the exercise, I'm going to start by showing you some examples of containers. So the most common repository for containers is Docker Hub, because most containers in the wild are Docker containers. But there are others. We have a Singularity Hub, a Singularity Library, both of which contain images in the native Singularity format, although I think Singularity Hub is being replaced by something else. So this may not be accurate for much longer. NVIDIA has their own repository, so if you like GPU-ready images, you may find what you need there. Quay.io is kind of like Docker Hub, but with extra features for developers. So if the container you need is particularly fancy, then it's possible the developers chose to host it on Quay.io to get access to those developer features. And then we have a Biocontainers repository, which again is similar to Docker, but it's mainly used by people in the biology department because there are so many different packages that a biologist needs that having a place to go and talk about them is really helpful for biologists, I guess. I'm not a biologist. We'll give examples of these other ones in the advanced section later. So let's go and look at Docker Hub. So this slide is showing you what Docker Hub looks like. If you were to navigate to Docker Hub, hub.docker.com, and search for a repository, you might see a page like this. So Docker Hub repositories are named in the form of a group, that's the people who created these images, slash the name of the image itself, which is similar to how GitHub works if you happen to be into Git revisions. And then there's also a group named _, but you omit that part because that just means it's published by Docker themselves and not by a group that registered with Docker. So that wouldn't be included. So in this example, there's a group of people who produce the TensorFlow software, and they produced a container that contains TensorFlow. So that's nice. We're going to use that later, not just yet. So within a repository, so we're still in the TensorFlow repository, there are multiple versions of this container, and the versions have tags to tell you which one is which. So you would search the tags for what you need. For example, if you're interested in the latest one, maybe it has a GPU support, maybe it has Jupyter support. If you're a Python user, these are meaningful to you. If you're not a Python user, then it's just a random string of characters. Now, some repositories will still work if you omit the tag. It will default to latest, but it's best to include it if you can, so that you know for a fact which one you're getting. Now, Singularity can fetch image files from repositories and also convert them to the Singularity file format at the same time. And here's the syntax, looks like Singularity pull, and then in square brackets, that's where you put the name of the file that you would like it to finally be saved on disk, and then a space, and then you have a source. The source has some syntax that says, this is where you're going to go look for it on the internet. And so, yes, you do want to include the extension of the file in the target file name. So when you come and look for it later, you'll remember what kind of file it is. So in the previous example, we were looking at TensorFlow from Docker Hub. So the source argument for Docker images looks like this: Docker : 2 slashes, the group /name syntax that Dockerflow itself showed you. If you're using a tag, another : followed by the tag. So this is not so very dissimilar to how things work if you were cloning a Git repository. It's similar. It's also, so in particular example, the TensorFlow example I showed you, it would look like this: Singularity pull, and then you pick the name of the file. I picked tensorflow.sif. That's not the best name because it doesn't tell you which version of this you downloaded. But for simple, this / just means this is all on one line. And this is the bash syntax for treat this as though it was all on one line. So it's TensorFlow space Docker : / TensorFlow : latest GPU Jupyter. Are there any questions about how to read this syntax? You will do an example very soon, I promise. The examples are coming. Okay. I told you that in order to do Singularity activities, we need to get an interactive job on a compute node. And there is a syntax for that. So our clusters use the Slurm scheduler. The Slurm scheduler, in our case, has a command srun, which is a variant of like sbatch. Sbatch is for submitting jobs. Srun is for getting a shell on a compute node. At least that's what we're going to use it for today. It technically can do other tricks, but they're not important. So the syntax you use for srun is very similar to the syntax you would use for sbatch if you've used sbatch before. So this would be the syntax for, I would like to reserve this much memory for this long on a compute node. And then PTY means pseudo terminal, which means the interactive job should connect you to that compute node in this way. There's technically multiple ways to do that. This is the way we want. And then when you land there, you want a terminal that's a bash terminal in interactive mode, so it doesn't just immediately exit and kick you back out again. It's quite a long syntax, but hopefully you can, after a couple of tries, type it in correctly. And then I also told you that you want to use Scratch for your Singularity activities because the files are large on disk. So the way to do that is to set this environment variable, Singularity _ cache dir, and you can pick any location in Scratch. So I picked $Scratch, which is just shorthand for the path to your Scratch directory. And then I decided to name the directory .singularity. So the dot just means it will be hidden by default. You don't have to if you don't want to. That's what I decided to do. So this is the typical thing you would do. Normally, it would put a .singularity in your home directory and it would overflow and you would have to figure out why you can't do anything. And export just is the bash for keep this variable around for a while. I'm going to need it. And then finally, compute nodes don't have access to the internet by default, but you can get access to the internet with module load web proxy. Web, the W and the P are capital. You only need this if you're about to do a Singularity pull command. You don't need it for most Singularity activities. So let me go ahead and get a shell on a compute node and do this live. You can follow along with me. So I'm on the Grace portal. I would like Grace shell access, please. It needs me to type in my password. It needs me to do my two-factor authentication. Bling. And then it says, welcome. Slightly off the bottom of this projector screen, you happen to be one of the very few people who are here live. And so for that reason, I am going to make my window just a little bit smaller. Okay, so the first thing I'm going to do is I'm going to go to my Scratch directory so that any files I create will be in my Scratch area. CD $Scratch. And then I happen to have pre-created a directory named intro containers. Can I spell? Not very well, apparently. Getting closer. I think that's it. No. Oh, you know what I did? I didn't use an underscore, I used a space. There we go. So now I'm in a directory on my Scratch space, so I'm ready to start doing Singularity activities. Let's get a compute node. srun launches interactive jobs on compute nodes. We need some memory, not a lot. We need some time, not a lot. Remember, you have to specify the minutes and the seconds, otherwise it will think you just wanted a minute. That will be disappointing. And then pty bash I. It says, oh, I missed a space. There we go. And then Slurm will say, hold on just a second while I find you a node somewhere. Okay, and now I get a new terminal, but this isn't the login node. Oops, host name. I'm now on the compute node number 241, which does have a Singularity installed there. So if I type which Singularity, it says, hey, I found one. It was over here in the USR bin directory. So now I'm ready to start doing Singularity activities. Not quite. I need to do these last two setups. Export Singularity cache. Okay. Export Singularity cache equals, and then this is where I decided to put mine. I don't have to do what I'm doing, but it is a very good idea to put it somewhere in Scratch. Otherwise, you will eventually run out of space in your home directory. And also, we want access to the internet, module load web proxy. Now I'm finally ready to do Singularity activities. So next on our slideshow, let's pull the Hello World repository from Docker Hub. It's very small, so this will not take long. Assuming you are following along with me and do have a compute node ready, it will only take a moment to download this very tiny repository. So I've already done some of these steps. srun, in this example, I requested more memory per node and more cores per node. That could be a good idea if you're working with a bigger repository. For this particular one, it's fine, because Hello World is a very small repository. So the next line of code we have to execute is this one. Singularity pull Hello World. That's SIF. That's what I chose to name it in this example. And the location of it is Singularity : 2/ Hello World. And you can omit the underscore because that just meant that it was published by Docker and not by a particular group. So let's try it. Singularity pull hello world .sif space Docker hello. Does it have an underscore? I already cannot remember. It is a hyphen. Hello hyphen world. If I spelled it correctly. Double checking. Believe I have spelled it correctly. So let's try it and see what happens. It downloaded a small file very quickly, and then it returned to the shell. So let's see what's in our current directory. Hey, there's a file. Is it the one I just made? Yes, it is from just now. Now that I would like to see how many people are following along. Please do raise your hand in the room or say yes in chat whenever you have successfully downloaded this container using Singularity pull on a compute node. A few people have said yes. I think it would be good for me to leave this text up on screen while I talk about the next thing. So let's see if I can figure out how to do that. Now, this is not what I wanted. Okay. Yeah, so my terminal doesn't remember what was going on the login node before I got to this compute node. That's hilarious. Okay, I can't put that syntax on screen, but I can come back to it in a minute. Okay, so the next thing we're going to do is I'm going to talk about how you would do the same thing in a batch job if you didn't want to do this interactively. Maybe you have a really, really big container you need to pull down and it's going to take like an hour and you just don't want to sit there. Well, you can do the same thing in a batch job if you're familiar with how batch jobs look like. This is just the typical batch job. Typical parameters like job name, time, tasks, memory, where the output file goes. And then you just put the same syntax that I put here. Go to your Scratch directory, set your cacher, get the internet. There's your Singularity pull command. And this job will do the same task without you needing to watch over it. Now, I've just downloaded an image, and I think you have also downloaded an image, at least some of us. But for the rest of the images in this lesson, they do exist on disk already. They're pre-downloaded. So if you want to, if they're taking too long, you can go and get the pre-downloaded copy and use that instead. So I have put them at Scratch Data Singularity images. They should be publicly viewable. You can make a copy in your own Scratch space. That's a little faster than downloading it from the internet. Here's an example of a container that's located there, Fedora 28 HPRC Lab. It's got a usable workstation. If you've ever used HPRC Lab, it should be pretty much the same as what was there at that time. This is an older one. .img is the file extension from an older version of Singularity. And describing these pre-built images also on our wiki. So let me get back to my terminal and navigate to that space and show you that it exists. Scratch data Singularity images. And there are several items here. We have the TensorFlow example, which I showed you earlier. There's one here. We're going to take a look at some of these examples later in the advanced section. So here's Ubuntu. That one is generally good enough for a lot of purposes. It's just got the libraries that an Ubuntu operating system would have. Not the whole operating system, obviously, because that would defeat the purpose of containerizing. Just the libraries that the Ubuntu machines typically have. So now that we have containers on disk, one that you downloaded, some more that are available, we're going to practice using containers. So the first thing to learn is that there's multiple ways to use a container. Basically, it comes down to what kind of task do you want to do. So if you want to have a shell and type commands, then then you can do that. If you want to execute a specific command, we have a command for that. And if you want to, if the container itself knows what it's supposed to be doing, then we have a command for that. So we're going to try all three of those. We're going to try the hello world image first because it's right in front of us. We already have a compute node, and if yours hasn't crashed, you don't have to do this because you've already done it. And of course, if you have crashed, no big deal. You can just get right back to it. We're going to try the run command first. So the Singularity run means the image knows what to do. Let it do the thing it's supposed to do. Hello world knows what it's supposed to do. I'm going to go back where I just was and do Singularity run hello world .sif. Okay, the message is quite a bit longer than I said it would be, but the hello world is up there at the top. Hello from Docker. Remember, we downloaded this container from Docker Hub. So as far as Docker Hub knows, this container is for Docker users. So it's hello from Docker. And then a bunch of more words that are not important right now. Telling you how to use Docker. We don't need to know how to use Docker. We're trying to learn how to use Singularity. Now on the other page, I showed you that there was another way to accomplish the same thing. Let's take another look at that. In addition to Singularity run, if your container file has execute permissions, now obviously you can use chmod to grant and take away file permissions, but if it does have execute permissions, then executing an image file means the same as do Singularity run image file. So let's try to make sure that's true. /hello world. Oops, I guess I should check if it has execute permissions. Yes, in this case it does. So Singularity decided that it was going to go ahead and preemptively add those. That's convenient. Let's test it. /hello world. Yep, it does the thing it's supposed to do. There you go. But that's all we can do with this image because the hello world is a minimal image. That is, a long time ago I said, the point of containers is to try to identify the minimum number of things that you need to bundle up in order for your application to do its job. Well, it turns out the minimum number of things for hello world is very small. So this is all the container can do. It can't do anything else. It doesn't even have a shell. What use is a shell in hello world? That would be shello world. Okay. So in order to do the next exercises, we're going to have to use a different image. Any old image will do. In this example, I used the Fedora image. I think today I'm going to use the Ubuntu image instead because I feel like it. We'll compare and contrast. We'll see if it makes a difference. So this image is at Scratch Data Singularity Images. So we're going to have to CD over there if we're going to use the pre-installed copy. Otherwise, if you want to go ahead and do a Singularity poll, it will work. It'll just take a minute. If you want to do Singularity poll Ubuntu, then you can get your own fresh copy. Otherwise, you can use the pre-installed copy. You can just CD over there and use it. You can't break anything, remember? Singularity doesn't give you extra permissions, so you don't have to worry about that. So the first step is get on a compute node. Yep, I'm on a compute node, so I can skip that. Now we're going to try the Singularity shell command. Let's go back where I was. Yep, here I am. Let's try Singularity shell. And I'm going to use the Ubuntu image today because I feel like it. Okay, now my terminal changed. Now it says, instead of saying, you know, my username, the node I'm on, the location, $, now it says Singularity right caret. That means you're now in a shell that's running inside the Singularity container. So the shell thinks that the files that exist are the ones that are in the container. So for example, if we're in an Ubuntu container, then there should be a file that says we're in an Ubuntu container. And that file is named etc. OS release. So let's see if there is one. Yep, there it is. And let's see what's in it. So in this Ubuntu container, you are allowed to read that file. So let's just check what the first line is. Ubuntu. Yep. Okay, so there is a file that is in the Singularity virtual file system. So when you're in a container shell, you can go and interact with that file. You can read it and see that this is the Ubuntu set of libraries, this file being one of them. Even though it's just a plain text file, I guess it still counts as a library. It's not the operating system, literally. What else did I want to do? I guess that's enough for now. So another shell command I know is exit, which means I don't want to be in a shell anymore. So whenever the shell exits, Singularity will return you back to where you were before. So in this case, I'm on a compute node. Now let's check if the compute node, the real file system, also has an etc. OS release file. Spoiler alert, it does. Oops, wrong command. So let's check the first file, the first line of that file. Aha, it's different. So on the compute node, this compute node is not an Ubuntu operating system. It is actually a CentOS Linux operating system. So that file, the literal file that exists in etc. OS release in the physical file system is different than the one we saw when we were investigating the virtual file system inside the container. If you have been confused the whole time, this example might help you understand what I was talking about. And you can see when I wrote the instructions up here, the OS release contained the name Fedora. That was a Fedora operating system. You can do pretty much anything in the Singularity shell that you normally could do. We may see some examples of that later today. Let's try the last method of interacting with an image. We've already tried run, and we've tried shell. Let's try exec, which is just run a single command immediately, and then you're done. So, for example, let's suppose you wanted to execute Python. Well, one thing you can do with Python is ask it what version it is. That's no big deal. Another thing you can do with Python is you can tell it to print hello from Python. If you're a Python user, this syntax will look familiar to you. Otherwise, it doesn't matter. You don't have to execute Python. You could execute any command that's in the container. For example, there's a bunch of shell commands in the container, like, I don't know, echo or something. In this example, I used the Fedora image because it had Python in there. So I guess I'll do that today. Try to mix it up. So let's get cracking. Singularity exec, and then the name of the image, and then now you type any command and hope, and then Singularity doesn't know if the command is going to do anything, but it will let your container try. So I'm going to try executing Python. What was the syntax? Python 3. Make sure it's Python 3 because I don't like Python 2. Let's ask it what version it is. That's not how you spell version. Here we go. So this image is quite a bit larger, so it takes a moment to load up Python. But it comes back and says, yeah, there's a Python in there. That's 3.66. Now for contrast, on my real local compute node, if you ask Python what version it is, there is no Python 3 on this machine. There's a Python 2 though. And if you asked what version it was, you would get obviously something else. I can't spell. Spelling is so hard apparently. Okay, so there's a Python 2 on the real local compute node, but inside the container, there's a Python 3. So that was cool. Cool little demonstration. I'm going to try the other one. Let's try something different. How about let's check a shell command inside that Ubuntu thing. So Singularity exec, the Ubuntu image. Let's tell bash. Let's tell bash to what should bash do? Bash should echo scratch. Ooh, that's a good question. What will happen if I tell bash to echo the scratch at me? Hey, it actually worked. So scratch is a what do you call them? An environment variable that exists in my shell, in my real shell on the local compute node. But according to Singularity, that thing also exists inside the oh wait, I guess I should have tried it like this. Let's try it with the single quotes, because if you're a real bash expert, you'll be complaining, hey, you didn't prove anything. Aha! Now that really does prove something, because when I put the single quotes there, that means the command I'm currently executing, Singularity, will not attempt to open and read what's inside there. It's just characters. So at the time I executed Singularity, that wasn't a variable statement, that was just a string of characters. It didn't get interpreted as a variable statement until the bash that's inside the container tried to read it, which means the bash inside the container does see the same environment variable that was outside the container. And from this, we learn that Singularity tries to respect your environment variables when it can. And in this case, it can, so it did. Working with files. The file system inside a container is isolated from the real physical file system. So if you want to access your real physical file system, you have to ensure that the directory is mounted. by default, Singularity will mount home and the working directory if it can. And if you need to specify additional directories, you can use the Singularity bind path environment variable or the bind command line option. It occurs to me that we've been here almost an hour without a break. So instead of doing an exercise, I will stop and we'll take a break. Let's go over this again. 5 minutes is a long time ago, so I assume you've forgotten. So inside the container, the file system is isolated, which means that if you want access to the files that are in the real physical file system, you have to specify that that's what you want, which is called mounting. A mount is a connection between a file, a directory inside and outside. By default, it will mount your current directory and the home directory. You could also tell it not to do those things. But you're going to need to actually mount a little bit more in some cases. So let's practice. So there's two ways to mount. You can either use the bind path environment variable or the bind command line option. So they do the same thing. Either way, you just provide a list of directories that you want mounted. So here's an example. First, you make sure you're on a compute node. We've already done that. And then if you're using the bind option, then you just add it in your Singularity command. So one thing you might do is, for example, let's suppose you wanted a shell, and in the shell you want access to the files in your Scratch directory. Singularity shell bind your Scratch directory, comma, other directories. And then finally, of course, because it's a Singularity command, you continue with your Singularity syntax. So Singularity shell image. Then you get your shell, and you can investigate whether you can work with files. So let's do this example. I'm going to do this example. Any container image will do for this example. So I'm going to do Singularity shell, and you'll notice that my working directory is not my personal Scratch directory. So there's no reason at all that my Scratch directory would be mounted. Actually, that's a good test. Let's try it without mounting it first to prove that I know what I'm talking about. Singularity shell Ubuntu, and then if I go to my Scratch directory /intro space containers. What? Oh, I forgot the quotes because there's a space. Unbelievable. Oh, and I added a slash like a silly person. How did I do that? What am I doing? CD Scratch. Where am I? Intro containers. Okay. Now I'm worried I might have said something incorrect. Touch out file. Okay, exit. So now that I'm out of that container, I'm back where I was before. Let's see if that was there. Intro containers. Autocomplete. Okay, so it does exist, which means that the Scratch directory did get mounted. Singularity by default doesn't mount Scratch, but at HPRC, it has been configured to do that. So what I said in the slide was true in general, but in particular at HPRC, it will also mount the Scratch directory, at least your Scratch directory. So in order to do this test, I'm going to have to pick a different directory. So why don't I test the temperature? Yeah, that's something that shouldn't be mounted, right? Because that's not Scratch. All right. So let's check that there is a temperature. Now I am in a Slurm job. I am in a Slurm job, which means there's a temperature. An interactive job still counts as a Slurm job. So it's hard to read because it's blue on black, but it says temp job and then dot and then a number, which is, I guess, the Slurm job number. So it's a directory that exists on the real physical file system. So if I do my Singularity shell, and then I try to check if that temperature exists. Oh, it does. Gosh dang it. What am I going to pick? I don't know anything else to check. So it has also been, so Singularity knows about Slurm and mounted the temperature also. So what I said was even wrong in a second way. Here at HPRC, Singularity will mount temperature by default. I'm going to have to pick a directory that it definitely would not mount by default. We got software. Interesting. Wonder if it's going to mount the software directory. It probably will. Okay, then I'm going to have to cheat. I'm going to have to tell it not to mount one of the things that it does mount by default. Okay, here we go. That's the syntax I need. So Singularity shell, no home. Don't mount my home directory. And then let's see if home exists. Does not exist. Perfect. Well, anyway. So then I'll do the Singularity and then shell. Now let's do no home, but then let's also tell it to bind. What was the syntax? Bind. Bind and then a list of directories. So let's tell it to bind my home directory. Oops. No, that's not what I want at all. Tell it to bind my home directory. And then the syntax for if you want to give it a different name is colon. So let's call it angry because I'm frustrated that my example didn't work. Ubuntu. Finish off the Singularity command. So now the home variable still points to nothing that exists. Let's see if there is a angry. There is, and it's actually, that's what's in my home directory at the moment. So perfect. So you do get to control where your files inside the container interact with files outside the container, even though most of the files that you might need are going to be mounted by default. And maybe someday I will move on from this exercise. Okay, so here's an example of if we were doing this in a batch job. Export Singularity bind path, scratch tempter to make sure they're mounted. I believe they are going to be mounted by default. And then if you want to change the name, you put the colon followed by the new name. So that's the end of the basic section. So if all you want to do is high performance shell computing, you are now qualified to do high performance shell computing with containers. But I assume you're here because you want to do research. So because this is the high performance research computing group. So that means you probably need more than just a shell to do your research and your high performance computing. And so I'm going to give some examples of doing a little bit more than just a shell in the advanced section. And since we have lots and lots of time, and you are my captive victims, and you cannot possibly walk out the door that's open or click the button that says leave meeting, and I'm just going to go ahead and do it anyway. All the slides I'm showing you are available on our website. So here's the course homepage, which is how you registered for this course. And you'll see that these slides are not here. Why are they? Well, they're supposed to be here. They will be here very soon. Maybe I need to refresh my page. Those were the slides from spring. The slides from fall are supposed to be there. But my page didn't get updated. So I'm going to open up that next slideshow. Where's my button? Here we go. Button. So the advanced section, I will cover some topics that may not apply to you specifically, but hopefully somewhere in here there's a topic that applies to you specifically. So we'll continue using the Grace cluster. I will anyway. If you want to do it a different way, then you can. So in this section, I will just do different examples for a while. And at the very end, I'll talk about building your own containers. Now, probably you didn't come here to learn to build containers because the whole point of containers is to let someone else do the work of building them. But I'll still talk about it. Here's, again, our learning resources. The stuff I show you today is on our wiki. That's this top link right here, hprc.tamu.edu/wiki/software. If you go to the main part of the wiki, then on the left panel, why don't we do it now? On the left panel, you will see there's a software button. That takes you to the software page. And if you scroll down a bit, you'll see that there is a Singularity button. And that takes you to the Singularity page. And a lot of the stuff here is literally what's in my slideshow. And then, see, here's an example that was in my slideshow. This one says Terra, but it was the same. So if you forgot how to do these examples, you can go to the wiki and get the same information again later. Richard, I forgot how to Singularity poll. Well, it was there in the wiki. I scrolled past it really fast, but that's where you go to get it if you don't want to use the slideshow. Slideshow's not the best for copying and pasting things. More containers exercises. So if you're a high performance research computing, maybe that means you want to use a GPU. I told you that Singularity natively interfaces with GPUs. Now I'm going to prove it to you. So here's an example. Here at HPRC, we have NVIDIA GPUs mainly. So in order to use NVIDIA GPUs, you create programs using the CUDA programming language. And that means that the container should have been built using a CUDA version that matches the local GPUs. So on Terra, the GPUs require CUDA at least 9. On Grace, one of the GPUs requires CUDA at least 11. There's another one that requires CUDA at least 10. Hopefully you don't have to worry about that because whomever has built your container is responsible for using the correct version of CUDA. And assuming that is the case, the only thing you need to do is add the --NV flag to your Singularity command. That's short for NVIDIA, of course. And that will tell Singularity that whenever it launches, it needs to go and find the local NVIDIA GPU, go and find the local CUDA libraries, and connect them to your environment. So where do you get a container that was built in this way? Many repositories on Docker Hub have GPU-ready images. So one of the ones I showed you, we're going to use it. That's where I got it from. The NVIDIA Cloud also provides GPU-ready container images. So I have a description of how you do that in the wiki as well. We're not going to do that one today, but it's there in the wiki if you want to go check it out. So today we're going to use the TensorFlow image that I showed you earlier. Let's check if it's still there. Okay, I'm currently in a Singularity shell. I can tell because the word Singularity is right here before my cursor. So I need to exit that because that was the Ubuntu image. So where am I? Oh, good. I'm in this directory where I have pre-downloaded the images for you to work with. So let's check if there's a TensorFlow that has GPU. Yes, there are 2 of them. TensorFlow 241 with GPU.sif, and also there's TensorFlow 241 GPU with Jupyter.sif. We'll try that one in a bit. First, let's try the plain GPU one. That's we're going to do a little bit of shell nonsense. So there it is. That image file I got from Docker. I showed you earlier a screenshot of where I got it. Now, in order to prove that the container can find the GPU, I have written a little script, and all it does is it basically prints out if there's a GPU. So that's no big deal, I hope. We can look at it if you like. We can read the code. It's not complicated. So in this example, we are going to need to be on a compute node that has a GPU. I'm not currently on a compute node that has a GPU, so I'm going to have to exit my Slurm job and get myself a new one with this syntax. This is the syntax that you would use to get a job on a GPU node. Oops, went a page ahead when I didn't mean to. Let's try to replicate this procedure on my shell. So I need to leave my Slurm job, exit. Now I'm back on the login node, and now I need to add the syntax to this to get the GPU node. So the syntax was, I already forgot. Syntax was GRES equals GPU:1. That means I need a specific resource. I need 1 GPU. GRES equals GPU:1 space. And also, you want to be in the GPU partition, so you're waiting in line with other GPU jobs and not waiting in the wrong line with all the non-GPU jobs. Partition equals GPU. This is the same thing that you would do in your batch file, except it would be, hash sbatch space and then that same thing. I can show you an example of that in a bit. Now, the GPU nodes are a little bit rarer, so it's possible you will have to wait a minute to get your job. If that's true, I apologize. We will wait for you if you are trying to keep up. The command. I think I can. Yes, that's a good question. Can I put this in the chat? So yeah, I think I can do that. Copy. Paste. Yep, I've just done it. So the command I typed on screen, I have just put into the Zoom chat. So if you are wishing to follow along and learn how to use a GPU, you can please do try this. I was able to get on a node. Let's find out what node I landed on. Host name. I landed on G65, the 65th compute node that has a GPU, I guess is what that means. So let's try to find out if Singularity can find the GPU. So let's go back to my example, check the syntax. So we're going to execute a specific command, and the command is test if there's a GPU, which means we need Singularity exec. We need to add the NVIDIA flag to remind Singularity what we're up to. We need the name of the image that has TensorFlow in it, because we're going to use TensorFlow's check if there's a GPU command. It's just an example that I happen to know about. And then the actual GPU command is, the actual test command is this one. But of course, it's not a proper executable, so you need to tell Singularity, use Python to execute this command. So the full command, Singularity exec nv TensorFlow Python 3 tfgpu test. See if I can type all that in one try. Probably not. Singularity exec NVIDIA TensorFlow. Oh, I'm in the wrong directory. Yeah, I forgot. When I kicked out of my session, I forgot to go to the data directory. So you probably have to go to the data directory as well if you're planning to not download this image. Singularity exec NVIDIA TensorFlow with the GPU .sif, and then the command we wanted to execute is Python 3, the test script. The test script is located in this directory as well. So I don't need to do like a path to the test script, because recall Singularity will mount the current directory by default. So it should be able to find it, I hope. It does take a moment because TensorFlow is not small. It has to load a quadrillion, that's an exaggeration. It has to load a pretty good number of files. It says blah, 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 something about CUDA, number of GPUs available, 1. I requested 1 GPU from Slurm, and TensorFlow found 1 GPU. I am not surprised, but I am grateful that it worked, because if it didn't work, I would be embarrassed. Okay. Let me just remind you that the test script is also in this directory. I created it specifically to do this exercise. It really has no value. No one would ever want this. But if you're doing the exercise along with me, there it is. Why don't we read it, since I promised you could? TF GPU test. What's in here? If you're familiar with Python, then this may mean something to you. Otherwise, don't worry about it. It says import TensorFlow, and then use the TensorFlow list physical devices function to count how many devices there are. It's going to come back with a list. I just need to know the length of the list, and then you print it. Not very exciting overall, very simple script. If you're familiar with CUDA, you probably could have written a bash command to check how many GPUs there are. But I'm not familiar with CUDA. So I just did something I happen to know how to do. Let's move on. So we've just shown that we can get access to a GPU inside a container. Let's do the same thing in a different way. Python, people like to do Python in, what do you call them? Integrated development environments. So Jupyter is an example of an integrated development environment. And here at HPRC, we support that. So how do we support it? We support it in the portal. Didn't I have a portal? Where'd my portal go? Oh, here's my portal. Where's my mouse? Mouse, come back. There it is. So in the portal, we have an app for using Jupyter. So I happen to be on Grace, so I have to scroll down to find Jupyter. So here's Jupyter. On Terra, that's what you would click. But Grace is new enough that we're still doing some testing and development. So actually, we're going to do the Jupyter Notebook, the testing version of this. So this has the feature we need. The feature we need is Jupyter with Singularity. So we're going to click on it. And it takes us to a page. So the page looks like this. In this page, you have to select what kind of environment you want. Most people are going to use Anaconda or some other module that provides Python. Both of these are an example of software that has been installed on the local machine by an administrator. But that's not what we're doing today. Today, you're going to bring your own software. So we click on Containers with Singularity. And then you put the path to the Singularity image file. Scratch date. Oh, good. I already typed it in on the previous day. Scratch data Singularity images, TensorFlow 241 GPU Jupyter. We want the one that has Jupyter in it. .sif. I'm going to go ahead and put that in chat because if you're following along, typing all that in is going to be a hassle. So soon, we plan to extend container support to other apps. This is the only one that's currently working. So you can choose any image file that contains Jupyter. Here's one that does because I put it there for this purpose. If you want to download a different Docker image that you believe contains Jupyter, you can try it. It'll probably work. So the example we're using is this one. And then here's the same page I already showed you. So you're navigating to the HPRC portal. Oh, I forgot to change it. It used to be Terra. I did Grace today. If you want to do Terra, it'll still work. Terra on-demand interactive apps, Jupyter Notebook. It should say testing. I forgot to change it. My bad. So if you're on Grace, then it's Jupyter Notebook testing. And then you select containers from the type of environment menu. That's this menu. You enter the path to the image file in this menu. And then you scroll down to the bottom and we're going to do GPU because, again, what are we doing today? We're learning how to use GPU. So you do have to click GPU from the node type. Let's go down here and do that. Node type GPU, yes, please. And then you're ready to launch. Now, Jupyter jobs do take a minute to start because it has to launch an entire server. Please be patient as your job sits in the queue. Please be patient as your job is session, blah, blah, blah. We just have to be patient. Okay, I have a button that says connect to Jupyter, which apparently landed on GPU node 068. Not bad. I'm actually going to go over to my shell and exit from this job so it doesn't eat up all of my service units. Because when you're on a GPU node, it does eat up quite a lot of service units. So if you have been following along, don't forget to exit your job when you're done before you eat up all your service units. So now we have this. You can click the button when you're ready. I'm going to go back to my slideshow. Oops, I went way too far. What the heck happened? Okay, I guess there's nothing else on the slideshow. We're just going to have to wing it. Connect to Jupyter. Connect to Jupyter? Yes. If you are following along, all you have to do is, for example, create a new Python 3 notebook. New Python 3 notebook. Anywhere will do. So how do we know that we're in the container? Well, if we're in the container, we would have TensorFlow, right? Import TensorFlow as TF. That's just some Python syntax. If you don't care about Python, you don't have to follow along. I'm basically just going to type in that same test script we had earlier. Yeah, let's see if that works. It should spit out some nonsense about CUDA. I just need this code. Copy and paste. Why do work when you can not do work instead? Okay, it says, it didn't say anything about CUDA, but it finished, which means TensorFlow exists, so that's a good start. Let's test if we can get access to a GPU. Yep, one GPU is available. Perfect. So that means that this environment, the environment of the Jupyter Notebook, is the same as what we previously had. We have access to TensorFlow, we have access to the GPU node, and it all came from that container. So I'm done with this example. So I'm going to leave and quit. Yes, close your tab. And just in case, you can click the delete button over here to kill your job so it doesn't eat up all your service units. Are there any questions so far about what's going on? Anybody who's choosing to follow along, raise their hand or type yes in chat. Okay, so some people may find that this is not the example for you. Maybe we'll get to the example for you soon. Is this the one? Yes. So I've shown you Singularity with GPU. How about Singularity with MPI? So there are several different ways to containerize MPI, which means the first thing you need to do is you need to check to see what choice was made by the person who made that container. So here's 3 ways that you can do it. There may even be more ways I don't know about. You can have MPI that's installed and run inside the container. So that would look like Singularity exec, name of container, image file. And then within that, MPI run, whatever you're doing with MPI. You could install MPI outside the container. That means the administrator of the local machine installed MPI. In that case, you'd run it from outside the container. So it would be MPI run, that would be accessing the MPI that is in the real local file system. Singularity exec, image file, and then what it is you're trying to do. Or you could try to go fancy. You could do MPI that's installed outside, but run inside. So that means you would have to inside the container correctly point to the location of an MPI that is in the real physical file system. So you might do something like bind the location in the real physical file system where MPI is located, and then give the path to it inside your container so that you know you're picking the right MPI. And all of these methods have their own pros and cons. None of them is perfect. So let me comment on them. The first method is probably the easiest because the person who built the container is entirely responsible for whether this is going to work correctly. So assuming they have any competence at all, this will work correctly. But it does not do a very good job of interfacing with the local hardware because the person who installed MPI in the container made assumptions based on whatever hardware they had at the time. So MPI would be optimized for that use case. Then you bring it to a different machine and it's no longer correctly optimized. It'll probably still work. It just won't be as good. Now this next one, MPI installed and run outside the container. MPI run Singularity. Okay, so this one means your local cluster administrator installed MPI. So it will be optimized for your local hardware. However, it may not be the same as what inside the container knows how to interface with. So that means you might have to do extra work to interface what's inside the container with what's outside the container because Singularity can't help you with that. And then for the third one, this is an example where MPI is installed correctly, and then inside the container it's running, which means it should interface with the program correctly. But then you have to do the extra work of setting this stuff up. So all three of these methods provide their own difficulties. I'm not going to tell you which one is right for you, but we're going to try one of them today. Okay? So LAMPS stands for something molecule something simulation. I don't remember. I'm not a chemist. Okay, it's some kind of chemistry program. And so I got an example which is MPI capable. I put it in the sample area. And then I also have the test input for LAMPS, which all it's going to do is like start up LAMPS, say, yep, LAMPS can do the basic thing it's supposed to do. And all we're going to do is try to figure out if it actually had the correct number of MPI processes running. We're going to ask for 4 MPI processes, which means we need a Slurm job where we have been allocated 4 cores. So the way you do that is like this. You add the ntasks argument to your sbatch parameters. And then whenever you're running, now in this particular case, LAMPS is expecting a directory named work to exist. It just has to exist. So we're just going to pick any old location that is safe to write files to. Tempter is a place that's safe to write files to. And we're going to bind that as the work directory. That's just a LAMPS specific thing. That has nothing to do with MPI. Now, but it is a common thing that happens with MPI is MPI needs to have a place to put temporary files. In the case of LAMPS specifically, it wants to put them here. And then, so it's Singularity run because this container already knows what it's supposed to be doing. Singularity run the name of the container. And then we're going to tell the container that we're trying to do the MPI run task. So it's going to use the MPI that's inside the container. Now I kind of said something weird because this kind of looks like MPI exec, doesn't it? It kind of looks like Singularity exec, Singularity exec, and then some commands. Well, yes and no, because this container used as an executable itself requires arguments, and the arguments are the command you wanted to run. So internally, it's like a bash script that does some stuff and then says, execute whatever commands were my arguments. And it needs to do that in order to set up the environment correctly. So whether you're going to use exec or run depends on how the container was made. This is an absolutely enormous line of text. I hope I can like copy and paste it to you or something. That's next example. Go back, please. Okay, here's what I'm going to do. I'm going to cheat. I'm going to end my slideshow. So now I can copy and paste because this is an actual document. Copy. Go back to presenting. Now I can paste this absolutely enormous command in the chat to save you all a little bit of effort. Okay, I think that's going to be all in one line, but I'm not sure. If that's not all in one line, you may have to delete some new line characters. Just be careful when you paste that into your terminal if you're planning to do that. So I said the first thing we need to do is first thing I'm going to do is I'm going to go to that directory I keep going back to because I keep forgetting that I wasn't there. Then I'm going to get myself a compute node with 4 tasks. srun n tasks equals 4. Time equals 1 hour, I guess. What was that other argument? Was it mem? I think it's mem, right? Mem. Okay, we need a little bit more memory this time because it is going to do a test job. Mem equals about 2 gigabytes. M, right? Capital M, I think that's what it looks like. PTY-I. Yeah, a little m. A little m will do. I don't know if big M will work. I just don't want it to fail. Let's see. I don't see any typos. Let's try it. Okay, now I am on a compute node. Which compute node did I land on? I landed on compute node 249. Now, let's check what we were going to do. We're going to try a Singularity run command featuring lamps to see if lamps can find all the cores that are available. I pasted the command in the chat, so I'm going to grab it and start pasting in here. Oh dear. Oops. Yeah, so pasting is a bit of a problem in the, what do you call it? This terminal, the shell from Portal. But I can at least put it in piece by piece. Let's see if I did it right. Singularity run bind. I think I need to delete these because those were there back when I had new line characters and I don't have them anymore. Stable. Okay. The Slurm process starter for OpenMPI was unable to locate a usable srun command in its path. That's not what I was hoping to see. Huh. Did I miss something? Did I miss something? I think this is a case of OpenMPI not working as well on Grace due to a specific bug. So I'm going to try to work around that bug. The bug is on our wiki. So I'm going to pull up our wiki and grab the answer. I'm guessing this is related to the bug. Grace. Yes, Grace. So I went to the Grace section of our wiki, and I'm going to find the batch processing page. So the batch processing page says, here's how you specify, and then it says, warning, these options are not compatible with OpenMPI, but I didn't use those. Well, maybe I need to not try it interactively. Maybe putting srun inside of srun was what was causing the problem. How much time do we have? It's 3:19. I think we should take a break. That's what I think we should do. I need a break. And I'll ponder if I can get this example to work. It worked on Terra. Grace has a thing where OpenMPI and Slurm aren't getting along very well. And there's a workaround for it. Apparently, it doesn't work for srun specifically. So I think what I'm going to do is convert the example into a batch job. And hopefully it will work in that case. But where's my thing that says it's time for a break? That seem accurate? 5 minutes break, return at 3:25. I'm going to try to convert my example into a batch command like this one. Copy. Let's test Slurm. I want to create, I want to edit the file by creating it. Okay. So 5 minutes, 4 tasks, 1 task per node. That is a lot of memory. This much memory instead. And then I'm actually going to direct the output somewhere else, so it doesn't end up in the current directory, because the current directory is not writable by all of us. It is at least readable. Okay, now let's go and grab some of those lamps commands. Looks like this, right? Singularity run, but this is where the backslashes are going to come in handy. Then I don't have to put it all on one line. Okay, S batch. No, I'm gonna need to exit my current Slurm job. Yes, exit the current Slurm job before you try to submit any new jobs. Let's make sure I'm on a login mode. Let's test that. S batch the lamps test.slurm. It says batch accounting active on Grace. Charging your account. Yeah, no problem. I have an account. I'll be fine. And then since it is a batch job, you can see how it does. Well, it's going to be done by now, probably. So let's check to see if it had any output. Scratch.
What is the whole thing in so it's covered in the infected skull. Oh no, okay.
This is just a new warning. That warning is supposed to be there.
Yeah,
What did I name that output? Wait a minute. What did I name that file? That output file. Scratch lamps MPI output. That's what I named it, right?
What's
Nah, the output should be both. It didn't go here, did it? No. Maybe I just spelled it badly or something. Doesn't seem to be there. Maybe it's something tricky. Like maybe the lamps intrinsically redirects all its output to a different file. Yeah, we'll just not do MPI for now. So we have other examples we can do that hopefully will work. So I couldn't get MPI to work just now on Grace. If you happened to be doing this exercise on Terra, it probably did work for you. If you want to go try it on Terra, it probably will work for you. Grace seems to be having some trouble with MPI at the moment. Haven't quite figured it out yet. But that's not Singularity's fault. So how about a biocontainers example? There's a pretty good chance someone in the audience is a biologist or knows a biologist or has heard of someone who knows a biologist. So here's an example of biocontainers. I found this biocontainer here. Why don't we take a look at that, see what it looks like. So Biocontainers is a website that has a registry. So this is the BC Bio Next Gen container, which has a whole bunch of stuff in it. It's like the deluxe version of a car with all the what do you call them? The add-ons, the non-standard things. It's a very large package of many things to do. So what you would do is you would click on packages and containers, and then it's going to show you, here's a package with no data. That doesn't seem right. Similar tools. Oh, there was a server error. I have to refresh the page, I think. If I click on packages and contain, yeah, here we go. So here we have tags. So this is very similar to Docker Hub. So we have a Biocontainers. The registry is named tools, and then the container is named BCBIO Next Gen, and then it has tags. So this tag is named 110A, and it says that if you want to use Docker to pull it, you would use this syntax, and it says quay.io. Wait a minute, I said quay.io was a registry earlier. Does that mean Biocontainers is just a funny user interface where the things are actually on quay.io? Well, in this case, I suppose it does. So we're just going to go ahead and click this button here to copy that to our clipboard. And we're going to come back over to our HPRC wiki Singularity page and read about how to use quay.io. Wiki, HPRC wiki. There it is. We're going to read about how to use quay.io. Software, Singularity, examples, additional documents, detailed examples, quay.io. So if you are pulling from quay.io, then you do this. Singularity pull, target file name, that's the same pull command we've already seen. Docker, you're kidding me. Remember, I told you Docker, quay.io uses the Docker file format. It's just a different repository. The repository has developer features. It's the same container format. So we're going to pull a Docker container. It's going to be located at quay.io. And then after that, you have the same group source tag syntax that Docker Hub had. So let's go back to our example. So here we have, if you were doing Singularity pull, you would Singularity pull Docker quay.io / biocontainers / how do we know that's correct? I had a clipboard. What was in my clipboard? So quay.io was trying to help us by giving us a hint. This is what they said to do. Format font a little smaller, please. 28 maybe. Yes, that's the same thing. So the Biocontainers page said, do it like this. Do it like this. And then our page says, actually, do it like this. So you just take the same thing and add Docker in front of it. Docker / and then the same thing. So that's how I downloaded this file. So then you would, if you wanted to make it do a thing, here's a way to make it do a thing. You can, there is a Python file in there, bcbio_nextgen.py. It's executable, so you can tell it help, and then it will tell you how to use it. And there's also a Python in there, so you can do Singularity exec, name of this image file, Python, and do a random thing. In this case, there's a module named PySam. SAM has something to do with, I think it's split and merge. I think it's for like genome sequences. You want to split and merge genome sequences, something like that. So it has that module, so you could do this and confirm that it has that module. We end at 4, right? Okay, I guess I have time to do that example. I'll do this example live. So let me bring back my terminal. So am I currently on a compute node? Yes, I am. No, I am not on a compute node. So let me get myself back on a compute node. Here we go. Compute node, please. Singularity. Execute. What was the name of that one? Biocontainers. Singularity exec. Am I missing something? BC. Starts with BC. Right? Yeah, starts with BC. I was just spelling it wrong. BC. Yeah, there we go. And then why don't we tell that BCBIO next gen to turn on and tell us what it does. Do you do anything? It said there's a file in there named this. And it says, yeah, I can do lots of stuff. See all the stuff I can do? Ah, I'm very impressed, little file. I'm very impressed at how many things you can do. So let's see if that Python module exists. So then you would go Python. You just type Python. Will you get a terminal? I wonder. Hey, I got a Python terminal. That's cool. I'm going to import PySam. Let's see if it exists. Yep, it exists. Let's print PySam. Who are you, PySam? It says, I'm module and I live here. Interesting. Thank you for the information. Does it in fact live there? Well, I'm no longer in the singularity. You can tell because this is not a singularity prompt. So if I try to say, you know, check if that file exists, no, it doesn't. It doesn't exist on the host file system. It existed in the container file system. So I'm just kind of repeating things you've already seen to help drive home the point. What is the point? I do not know. Okay. Before we move on to the next example, I just want to try one more thing. Singularity shell Ubuntu. So I'm going to touch a file. Let's see. Can I touch a file? What if I do this? Is that going to work? Oh, read-only file system. Nope. Okay. Okay. So we do know that there's a couple options. Let's say I was to touch a file in my scratch area. I've already tried that, right? So that's going to create a file in my scratch area. Let's say I want to touch a file that's in somewhere I don't have permission to write. So we know there's a, what was that path I did earlier? Yeah. So we know that's a place that exists. What if I try to put a file there? No. What? Oh, because it's Ubuntu. I went to the wrong container, and I apologize. So what if I try to put a file here? Read-only file system. Okay, so containers, here, there's two options. The first one, I created a file that was in the real physical file system. And in the second one, I tried to create a file that was in the virtual file system, and it reminded me, no, images are read-only. So if I wanted to like install some stuff in a Singularity image, the way you might do in a Docker image. In Docker image, you can open the container, install some new stuff, save your work, commit, and then you get a new container that's got new stuff. Well, Singularity, that doesn't work because Singularity images are read-only. They're read-only so that they're safe to use on a cluster where multiple computers might be sharing the same file. So what can you do? What can you do? The next example, Singularity with a writable file system. Problem, you want to save your work or add things inside the container, but not the real local file system. So why might this matter? Here's an example. Let's say you have an application that creates millions of files. Well, on a shared cluster, millions of files could be a problem. For one, you'd be putting a lot of load on the file system, which might impact other users trying to use the file system. And number two, you have a quota. If you run out of quota, you can't create any more files. The people who use Docker containers, they did not foresee this problem because they work on their personal machines where there's no quota, there's no one to share with. So we need a way to actually handle this type of situation. Now I've shown you that Singularity images are immutable. The file system is ephemeral. So how do we add anything to it? So there's a solution called it's a second file, not the original image, which we agree we cannot change. The second file called an overlay that is user writable. So now I'm going to teach you how to use an overlay. So in order to create an overlay, basically what you're going to do is you're going to create a virtual file system in a file. Now this is a normal thing a Linux expert might do. So there's Linux tools to do this. DD and MakeFS create virtual file systems inside of files. But Terra and Grace have the wrong version of MakeFS. That's unfortunate. Not to worry, there's a container for that. So the Ubuntu container does have the correct version of MakeFS. If you were downloading it from scratch, this is how you would download it. We already know it's downloaded in our example area, so I'm just going to use the one that's already there. If you had a personal machine that did have the correct version of MKFS, then Singularity can create the overlay for you. So there's a Singularity overlay create command. You would just look up the syntax, and Singularity would use your version of MKFS to do the job. But since we don't have it, we're going to have to work around it. So here's how we work around it. If you don't have Singularity on your personal machine, this is how you do it on Grace. Oops. So on Grace, first of all, you got to get yourself on a compute node. Perfect, I'm already on a compute node. Second of all, you have to get a image file that does have the correct MKFS. Well, I've already got one of those. And then you just get yourself a shell and you execute these commands. If you don't want to get a shell, you can put the commands in a script and tell it to do the script or however you prefer to. They're just bash commands. So if you're comfortable with bash, there's like a million ways to do this. But this is how I'm going to do it right now. So the commands, there's a bunch of commands. I don't really want to teach you how they work. I'm just going to say, like, if you need to remember, you go to the wiki and you look it up. Stuff's going to be in the wiki, right? Which one did I load? Did I load Ubuntu? Oh, I did. I'm already in Ubuntu. Perfect. Perfect. So I'm going to go to my Scratch area because I need to create a file. Scratch intro containers. Oh, what the heck? Stop putting a slash there. Okay, there's the hello world that I created earlier. Now I'm going to create an overlay file. So let's start following these instructions. I have to make two directories. I have to have a directory named overlay temp, and it needs to contain an upper and a work directory. You can make all three at once using the -p syntax. What is this? Overlay temp. So this is just a space where some working stuff goes. One of them was named work, right? What was the other one named? Upper. Okay. Perfect. Next, we need to create a file and fill it with zeros because it's an empty file system. So we fill it with something, fill it with zeros. So in this example, we're going to fill it with 200 megabytes of zeros. So DD is the just, you know, bleh, some stream into a file. So we're going to get zeros from the zero device. We're going to put them in the same overlay thing. Oh, we're going to with the overlay file. The final overlay file is going to be named my overlay. So we're going to start filling it with zeros. 201 megabytes. DD in file equals dev 0. Out file equals my overlay. This is the overlay file. It's going to be named my overlay. If you want to name it something else, you just name it something else. Count equals 200. Block size equals 1 megabyte. If you don't know a lot about file systems, probably just leave it the way it is. Okay, it says it copied a whole bunch of bytes. And now there's a my overlay file. And then the last thing you need to do, and then you have to make the overlay file into a file system with the makefs command. And in this case, we're using the ext3 file system format. And we're going to use the two things we've done, the overlay temp directory and the my overlay file full of zeros. So I already forgot. D for directory. So the directory is the overlay temp directory. And then the my overlay is the file that's going to be the overlay file. Okay. And it says segmentation fault. Why did it say segmentation fault? Can't check if file system is mounted due to missing mtab file while determining whether my overlay is mounted. I do not even know what that means. You know, this is really annoying because this worked for me last week. I did this last week and it worked. Okay, someone else said they're not getting that error. Maybe I should just try again. Did I have a typo? MKFS ext3 overlay temp, my overlay. Oh, still segmentation fault. Can't check if file system is mounted due to missing mtab file. What is an mtab file? Okay, what if I just go all the way back out and try again? Sometimes you have to do some nonsense. Let's get a new Slurm job. Let's get a new Singularity shell. I'm gonna go to my directory, see what's there. Overlay temp, my overlay. Makefs, MKFS, did I spell it right? MKFS, ext3. No, it will not let me do it for some reason. Okay, well, maybe it worked for somebody. If this worked for you, I'm very happy for you. Maybe if you're on Terra, it worked for you. Maybe Terra is just the more cooperative cluster today. If it didn't fail, then you will have an overlay file that is of size 200 megabytes. It will be named my overlay. And then you just can remove the overlay temp directories because we don't need them anymore. So how do you use it? Well, if I had one to use, this is what I would do. You obviously would be on a compute node. And then whenever you are doing any Singularity activities, so for example, you might do Singularity shell Ubuntu, which is what we've done a lot of today. Then you just add the overlay argument, -- overlay space the name of the overlay file. So in this case, it would be overlay, my overlay. And then when you're in that Singularity shell, your file system is no longer read-only. You can create new files. You can make a directory, you can touch a file, you can exit. And then the next time you use that overlay with that container, that file will still be there. So the files then persist. They live in the overlay file rather than in the immutable Singularity image file. Keith suggests ls etc mtab. Shall I try it? No such file or directory. Is there supposed to be a file there? Okay, it says there's usually supposed to be a file there. Okay, so we have a question in chat. Will Grace treat my overlay as one file? Yes. So against your file quota, my overlay counts as 1. And every time you write data to it, Singularity opens the same file, writes a few bytes, closes that file again. So as far as Grace is concerned, it's one file, and then you have to do a few file operations to it once in a while, but not millions, because Singularity will open the file, write multiple virtual files to it, and then close it again. So then it's not as many file operations, which means it's easier for the file system to handle that load. So that is the point of doing it like this. I think if I landed on a different node, maybe there would be an etc mtab file, and it would work on that node. It worked for me on a different node last week. It worked for someone in chat just today. So I guess I can't explain why it didn't work on this node just now. But if you happen to be following along and you can get any of this to work, I would be very happy if you would report by raising your hand or saying yes in chat if you got this to work. So this is if you did Singularity shell, my overlay, then you could create files, and when you came back, they would be there in the overlay. So got a different error. Okay. I apologize for the inconvenience, the technical difficulties. I did not anticipate that this would not work because it worked for me last week when I tested it. And it is supposed to work. So I do not understand what is causing the errors. I will update the wiki whenever I figure it out. So if you come back in a couple of weeks, you will find answers on the wiki. There is a few minutes left. I don't have time to do an exercise about building a container because obviously that would take a long time, but I can at least talk about building a container. So generally speaking, the way that you would go about building a container is there's a couple of ways. So first of all, Singularity can build containers as well. So one way you can do it is you can create a Singularity image that is not immutable. So the image format we've been working with, the SIF, is the immutable flat image format. But there's another kind of container that Singularity uses called a sandbox. Instead of a file, it is a directory. And so you can create a sandbox instead of a flat file. Then you load the container as though the directory was your image. And then you can make changes to it the way you might in Docker. And then whenever you exit, the directory that contains those things will be persisting. However, although this method exists, it's not particularly useful because installing software usually requires root privileges. Even in a Singularity container, you don't have root privileges because we have to protect the cluster. So you would have to do this on your personal machine. If you are doing this on your personal machine, then you may not have Singularity, you may have a different container. Maybe you have a Docker. So in that case, you would just use the Docker equivalent of this, which is Docker load a container, make your changes, save the container. So here's an example of some syntax you might do. You have to use the writable flag when you want to actually work with a sandbox. And then whenever you're ready to convert it into an image, that's a flat image file, you would just use the build command to change its file type. Singularity can also build containers from a recipe. So this is also a way that you might build a Docker image. There's something called a Docker file. The Docker file is basically a recipe of here are the steps you need to do to make the container. The steps look like start with a basic container, put an operating system there, install these softwares, and then decide what the run script actually does. That would be a Docker file. Singularity has the same thing. You have a Singularity recipe file, which you have some options. You can have a bootstrap option, which says start from another existing image and add more stuff on top of it. You can say install these softwares into it, and then you can define a run script, which corresponds to the same thing that Docker has. And then you would just use Singularity build, except instead of a source like from the internet, you use a recipe file. And again, if you're using Singularity or Docker, both cases, you need the root permissions to build these, to install softwares in these containers. But if you were going to do it at home, then you might use Docker instead, which is fine because Singularity knows how to read from a Docker registry. We already saw how you would pull from a Docker registry. So if you're building from Docker at home, you would simply commit your container to a Docker registry. But you can, if you're building with Singularity at home, you can commit your recipe file to a Singularity registry, and some of them can automatically build the corresponding container using the same Singularity build syntax that you would do at home. They do it on their computer for you. So all you have to do is create the recipe, and it can do it automatically. Now, I'm not sure if this is going to continue to be supported because Singularity Hub is being replaced by something else. So maybe in a few weeks, this won't be accurate anymore. So I wouldn't waste a lot of time on that unless you're really sure that it's important to you. So that is the end of the advanced content. I just have to do some wrapping up. So the conclusion is, yes, you should run containers on clusters. It's easy, except for the things that didn't work for me today, which I will figure out and get back to you. But at least the basic stuff worked today. It wasn't until I tried to do advanced stuff that I started having problems. And we're supporting Singularity. We're expanding our support to more apps. So if there's something you would like to do with a container and you did not see, just ask, and we'll be very interested to help you. If you're used to Docker, you can convert your Docker to Singularity. And Charlie Cloud is on our list of runtimes that we're interested in supporting. So if you have a reason to want to use Charlie Caloud, you can expectingly wait for that. And also ask for help. I'm currently helping someone with Singularity right now. So if you would like me to do that, just ask. So there's a survey. The survey is not ready yet. I suppose we'll probably send it out early next week. The survey will let us know how you feel about this short course. If you like to give feedback. Are there any questions? There's only a couple minutes left. You can answer a question like, where do I go to get help? That kind of question. And I believe the next slide is going to be a repeat of where do you go for help? Well, the first thing you should do is go to the wiki, because we have a wiki that explains how to do Singularity things on our cluster. And if you don't like to read, you might find it on our YouTube channel. And if you really do like to read, then you could go read the Singularity manual. And if you like to take short courses like this one, here are some other short courses. These are quite good. If you follow along with their instructions, you might learn how to do something new. So that is the end of the course. It is 1 minute to 4 o'clock. 4 o'clock is your dismissal time. Thank you very much for joining me today, and I hope to see you again.